Hello, and today we're going to be talking about GCSE revision questions for heat transfer. That's for the Unit 1, the Year 10 exam. So if I share my screen with you, we are looking at a mixture of higher and foundation questions. As you'll see, the first one here is I've put the foundation, and to one side I've put the higher equivalent, so that you can see that by revising both, it will be helpful. So a group of students, let's get straight to it. We've got a lot to do this session. A group of students investigated different methods of heat transfer. And to remind you of the different sorts of heat transfer, there's conduction, convection, and radiation. Conduction in solids only. In convection, it's in gases and liquids, we say fluids, and in radiation, it can be through transparent materials, translucent materials, and through space. It doesn't need particles to transfer. Okay, so let's dive straight into the question. A group of students investigated different methods of heat transfer. First, they added a purple crystal to a beaker of water and heated it up as shown. Circle the method of heat transfer that was being investigated. So they've used the purple crystal, and that purple crystal, if I get a purple, I wonder if I have got purple. Yes, I have. This purple crystal will kind of like diffuse into the water. And because the water is heated down at the bottom, becomes less dense, that will start rising. And then the colder water will come from the top and sink. And the hotter water here at the bottom will rise because it's become less dense. So this is a lovely example of convection currents taking place. Okay, and what they want then probably is state what the students observed. You may add to the diagram if you wish. So what we have is we have a convection current set up where the hotter water becomes less dense and the colder water sinks to take its place, and you get a convection current taking place. And the purple dye will rise and then sink eventually to form this lovely convection current. So purple dye rises, showing that's what they want. They want you to say what happened, and then you can give your reason, because hotter water is less dense and rises. Okay. In their next experiment, the students placed 4 metal rods on a tripod. The rods were identical, except they were made from different metals. They attached a drawing pin to the end of each rod with Vaseline. They heated the other end of each of the rods and recorded the time for each pin to drop off. And the students recorded the following results. So iron took the longest, copper took the quickest. So therefore, the heat traveled from one end all the way to the other end by a mixture of atoms vibrating and electrons colliding into other atoms, and by conduction to the far end where it melted the wax and it dropped. So the lowest time for it to conduct would be the copper, so that would be the best conductor. And then you just put them in order, leaving iron last. So let's finish that off. Aluminium is next, and brass is third. Okay, now the higher equivalent of this asks you to do a little bit more with this particular one. It's asking how the apparatus is used. So basically putting into words a plan of action, how the apparatus is used and how the results are used to show that copper is the best conductor. So we heat one end, we put Vaseline at the other end and allow the heat to conduct along the bar until the Vaseline melts. The one with the quickest time will be the best conductor. And then it asks us in a little bit more detail in terms of what are the particles doing? And the particles will be vibrating. Now there's 2 marks here. The atoms themselves, which are in fixed regular arrangements, where it's hotter, they vibrate more. So atoms near heat source vibrate more. So this knocks in turn knocks to a neighbor atom, which vibrates a little bit more, and it so on and so on all the way down the chain. Also, though, you have the electrons, they gain energy and they move much faster. They've got more kinetic energy. They collide into the atoms and they create heat energy that way in terms of making the atoms vibrate by colliding into them. So you can see how higher it's much more involved and deeper in terms of what you've got to explain and how and the method you have to explain and what's happening to the particles in a little bit more detail. Let's go back to the higher version. So it says here, explain why the coloured water moves in the way that it's shown. So it's putting these two together. You know, the coloured water rises, all right, and because hotter water is less dense, it rises. The colder water sinks to take its place, forming a convection current. Explain why it's not suitable to put a hot radiator at the top of the wall to warm the room, because hot air rises. So you're not heating all of the air in the room if you just have a convector heater at the top, or a radiator, sorry, at the top, so that it'll only heat the top bit. So what you want it to do is heat the whole air and create this kind of convection current, so that you want it at the bottom. So it's heating the air at the bottom, and that is forced to rise because it's less dense, takes the colder air at the top, which then sinks to take its place. So you're heating the air in the whole room. Now I've added the mark scheme there if you need to have a look at more detail, but I'm going to move on because there are so many varied different questions. And this heat transfer module scores the worst scores out of all of the GCSE questions for Unit 1. It seems to be a concept of conduction, convection, and radiation. They're difficult enough to get, as well as being able to apply them in different situations. And they really want you to be able to apply the knowledge that you've acquired to the specific question in front of you, and not just rote learn these things. Okay, so the diagram shows a solar heating panel that is installed on a roof. The liquid in the solar panel becomes heated by radiation from the sun. The heated liquid passes through coils of copper piping inside a heat exchanger, resulting in water heating up. Explain in terms of particles how heat energy conducts through the walls of the copper piping in the heat exchanger. So it's through the copper piping, and that is a solid. So we have to talk in terms of conduction, all right? But it wants it in terms of particles. What are the particles doing? So in conduction, you have got fixed, regular atoms that vibrate more. They're already vibrating. The only temperature they don't vibrate is at 0 Kelvin, at absolute zero. But so at room temperature, or even, you know, kind of outside temperature, they are still vibrating, but just not very much. So when the radiant heat from the sun is radiant on to the glass cover and it goes through to the copper pipe, it's warmer than the copper pipe. So it makes those particles in the copper piping vibrate more. And that knocks on to the vibrating atoms knock onto neighboring atoms. All right, you just got to look at it like a domino effect. Once one is vibrating, it knocks onto the next, and that vibrates, and that knocks onto the next. And that's how it transfers down and through the copper solid. Don't forget though, this is 3 marks, so we do need kind of like something more than that, and we need to say and so on to give the idea that it cascades from one particle, vibrates more, knocks onto the next, that vibrates a little bit more, and so on. And then we've also got electrons, and they will move faster. And if they move faster, they will collide more with atoms down through the copper bar. Collide more with the atoms. And it's that transfer of kinetic energy with those atoms that makes those atoms have more vibrational energy, i.e. they will be hotter. Explain why the liquid in the solar panel circulates in the direction shown. Well, the liquid inside will heat up and that will become warmer. So warmer water, you can say hotter because it is that, but it won't be boiling. But warmer water is less dense and so rises and allowing for colder water to take its place, to take the place of where it was. And that forms a convection current in the direction that they've shown with these arrows. So the hotter water will rise up here and the colder water will come in here and it forms this convection current. In good sunlight, each square meter of the solar panel receives 960 joules of energy per second from the sun, but only 1/3 of this energy is used to heat the liquid. So we can divide that by 3 because only 1/3 is getting through. And it says calculate the amount of energy given to the liquid per second if the panel has an area of 2 square meters. This is for each square meter. So if we times that all by 2, then we can get it for the 2 square meters. So 960 divided by 3 is 320 joules. And then just times that by 2 is 640 joules. Okay, nice little foundation question here. Peter carries out an experiment to find the density of iron. He uses a balance. Now, if you were doing higher, they would probably say, Peter carried out an experiment to find the density of iron. Describe a method to do this. And you would basically put all of those different stages in. Okay, so stage 1, he uses a mass balance to measure the mass of iron. Look, they've given us some information there, 39 grams. He fills up a displacement can. Now, a displacement can, you can do this 2 ways. You could have put some water, say, up to a 20 centimeter square, it doesn't matter, cube mark. You could put the piece of iron in to that if it fits, and then it will go up to a new level. Let's see what that goes up to. That goes up to 5. So that will go up to, say, 25 centimeter cubed. So therefore, the difference here is the volume of the piece of iron. And I have to say, this is how I do it with my guys, instead of doing displacement method, but this is perfectly valid because you just drop the iron core into the displacement can, which is filled up to the spout, and then the water pours off, and then the volume that you get, the water that is displaced, is that water there, is the volume of the iron. And so that's reading off at 5 and I think it's centimeter cubed. They haven't, they might have it. I might have just got it off. Yeah, I think that's centimeter cubed. Okay, so use the information from the diagram to answer the following questions. So what's the mass? The mass is 39 grams. What's the volume? The volume is 5 centimeter cubed. That helps, all right, because I can't read that. And use the equation 39 divided by 5 to give you the density. And the density turns out to be 7.8. Now, put the working in the space that they have provided. Always like to do it near the equation. Repeat it down here so that you can secure your marks, 7.8, and then just pop the answer on the answer line here. And, oh, they haven't given us units. But the next question is underline the correct unit they should use for the density. Well, you've got grams here. You've got centimeter cubed, grams per centimeter cubed. Okay, will be that one. Okay, because volume is in a cube, centimeter cube, length times length times length. State one change to the apparatus that would improve the accuracy of the measurement of the mass of iron. Well, they want it on the mass. Maybe you could use a mass balance with greater resolution. So, for example, that would be 39.1 or 39.2, i.e. you can read it to the nearest 0.1 of a gram. So we could use a greater precision, you can say, instrument, mass balance, or you can use the word greater resolution, or you can say, if you don't like all of that language of resolution and precision, not familiar with it, you could say to read to the nearest 0.1 of a gram. Okay, moving on then. A pupil sets up an experiment to investigate the absorption of heat radiation. The diagram shows the apparatus set up before the heater was turned on for 8 minutes. 2 identical aluminium cans were both filled with 200 centimeter cubed of water, and a digital thermometer was inserted through a small hole in the liquid, in the lid. In the experiment, several variables were controlled in order to make a valid conclusion. In your answer, include 3 variables and an explanation of why each was controlled. There's so many different things. You want 3 of them. You could choose the same distance, okay? You could choose the same initial temperature, but each time you pick one, just write the reason for why it's doing it. Now, I've included the mark scheme here just to be a little bit quicker. So both the same cans, i.e. 5 centimeters from each other. So you stated what's the same, because the control variable is what you keep the same. Why would you do that? Because if one can is closer, then it would be heated more than the other one that was further away. Okay. In the side, you've got the same volume. If you've got the same volume of water, that's a fair test there. You want that to be constant because you're only changing the surface of the can, silver can and black can. So you want the same amount of water in each. So same volume of water you could choose. If they're different volumes, then the temperature rise would be different because you've got different number of particles inside receiving the heat energy. Same starting temperature, i.e. 8 degrees here. Does it say that anywhere? It doesn't say that. Oh, yes, it does. We can read it from the thermometer here. So 8 degrees there, 8 degrees there. So you're getting the information from the diagram. I didn't see that straight away, but I see it now. So different starting temperatures means that it rises by, to different, you can't compare it, can you? And you want to be able to directly compare it. And that's 3, but there are more there. And it's about you being able to structure it. So if I were you, I would bullet point, but without the bullets. Just do it so that, in your mind's eye, you are starting with a capital letter and finishing it with a full stop. And you're putting a reason for each of the variables so that you're linking each one of them. Each minute, the temperature of the can in each. I can imagine with that particular experiment that it wouldn't have been scored very well on that QER. Any QERs with conduction, convection, radiation, it just doesn't score very highly, because I think that candidates aren't very confident with the concepts of applying conduction, convection, radiation. Each minute, the temperature of the water in each can was measured. The data for the silver can have been plotted, and its best fit has been drawn. Apart from one result, the data points for the black can were also plotted. At 5 minutes, the water temperature in the black can was 25. So you want to be writing, plot this missing data and add the line of best fit. So you're going to get 1 mark for the plotting. So you go along. Now, if I were you, well, it's easy for me because I can expand that and follow it along, even though my eyes aren't particularly good as you. 25 there. I hope I've got that right. And then put the cross, neat cross, not a football. Well, they've got a blobs, but you're going to do it as a neat cross. And then literally, I would turn your exam paper around now so that you've got, and it's a little bit difficult because I'm attached. All right, and then just literally your elbow wants to be in the center of the arc, and you just look to the next one. It's going to be difficult for me because I'm doing this electronically. Keep going, keep going, keep going, keep going, keep going. It's not bad. I don't know if the examiners would give me that because it's a little bit, but it's a smooth curve. It's got no joins, it's got no hairs, and it's going through a best fit of all of them. Okay. Compare the temperature rise in the black can with the temperature rise in the silver can. So the temperature rise in the black can here, we're going to have to label this up to get our mark for the line of best fit. Okay, is much greater because we've got the same starting point of 8 here. And with the black, in 8 minutes, it goes up to 50. So that's 50 take 8 is 42 degrees. Okay, and with the silver can, it goes up to, let's just check that, that's 40 degrees. So 40 take 8 is 32 degrees. Okay, compare, so compare the temperature rise with the temperature rise in the silver can, but we need to actually compare that. It's not good enough for you just to work it out. You need to say that the black can for 42 degrees is larger than the silver can. You need to actually state the comparison. Okay, so what does that mean? That the black surfaces are better absorbers, because what's happening is that this black can here is going up to a higher temperature and the heat is in the middle, and those black surfaces are receiving the radiation, so they're absorbing the radiation in the black can a lot better than the silver can. So we can say that black surfaces are better absorbers than silver. Always got to be comparing it. Okay, silver surfaces. Okay, so have a look at this one. Higher question. All right. Exactly as I predicted in terms of if it's higher, you would have to choose your apparatus, you would have to say your method and how you would measure the density. So you need a mass balance. I'm going to put this over here and talk you through this. Okay, you need a balance, you need a measuring cylinder, or you can use the displacement can like I've shown you before. A description of your method, so weigh the rock, record its mass. Fill a measuring cylinder, okay, up to a certain amount. I just chose 20, they chose 20 as well. You don't have to choose 20. Record the volume and then put the rock in without splashing any water out and measure the new volume, and then take the two measurements a way to find the volume of the rock alone. And then to calculate the density, you use the equation density equals mass divided by volume. Okay, so density equals mass divided by volume. Take the recorded mass, take the calculated volume, and divide the one another to get the density in grams per centimetre cubed if you've done the mass in grams and the volume in centimetre cubed. Okay, so that's just to show the difference between the higher and the foundation, but equally they could give foundation level that question as a QER to do. Now this moves on to triple foundation and higher questions now. But this wasn't a triple, but this does apply to the double awarders still. So listen in and I'll say when you can cut out, because this is looking at experiment 1. You've got the heater in the middle, you've got the black surface and the silver surface either side. So that is looking at absorption of radiated heat. Experiment 2, you've got a nice little block, I can't remember the name of it, it'll come to me, a little block with different surfaces, so that, and you've got an infrared camera so that it's measuring the heat of that surface for the black surface, for the silver surface, with a few results, and that's showing the emission or the ability to the silver and the black surfaces to emit radiated heat. Okay, so experiment 2 is to do with emitted radiation. Use the data to complete the following sentence. Now this is foundation and this is what to expect on foundation, but they might just ask you to explain the results. The something surface is better emitter of heat. So look at the experiment 2, okay, and it's the black surface is higher. So the black surface is a better emitter of heat, as shown as by the results for experiment 2, because the temperature is higher for the black surface. All right, whereas the something surface is a better absorber. So again, don't get caught out. Black is not just a good absorber, but it's a good emitter. So the black surface is a better absorber, as shown by the results for experiment 1, because the temperature is higher for the black surface. Okay, so it's a bit of a tricky one, because having put the black for one, you're tempted then to use the other one, a silver surface for the other one, and it's not the case. Silver coating can be put on the, you can use it the same, again, and don't get caught like that, because you can use it more than once, an answer. Silver coating can be put on the outside of windows to help to keep houses cool in the summer and warm in the winter. State why the silver coating helps to keep the house warm in the winter. Now, right, so watch for this. So you know that the silver surface is a good reflector of heat back in, but we say it's a poor emitter out. You know that black surfaces are better at emitting heat energy out, radiated heat out. So we say that silver surfaces are poor emitters. So we can say silver surfaces are poor emitters, because you've got to think where the heat is. The heat is inside the house, it's trying to get out. So it's trying to travel from inside to out. So therefore, the silver surface is a poor emitter. It's preventing heat loss, because it's a poor emitter of radiated heat. You can get your mark still for saying that it reflects heat. As long as you say it reflects heat back into the house, because the house is where it's the warmest. A saucepan, another triple, but equally, this could be used in double because it involves conduction and convection. Explain in terms of particles the processes of conduction through the metal base of the saucepan and convection in the heater. Now, conduction happens in solids. So let's run through it with this here. Okay. Now, as long as you address all of these points, okay, for conduction. So conduction happens in solids, and it happens in the metal base, and it happens in that copper. As long as you relate it to the specific question, then you'll get your marks. So the atoms, they gain energy from the gas heater here. And in gaining energy, they vibrate more. And in vibrating more, they knock onto their neighboring atoms. They collide, they knock into them. All right, they're not traveling into them, they just knock. It's like if you have your partner next to you and you're vibrating a little bit more, you'll knock on a little bit to the next person, and they'll knock on a little bit to the next person, and so on. So we say that the particles, the atoms, they vibrate more or they vibrate faster. And that means that the energy is passed on by those collisions of one atom vibrating and colliding with a neighboring atom, and so on. But you've also got this idea that free electrons, so the atoms are fixed. They're in a regular arrangement. And it's because they are close and in contact with one another. If they vibrate more, they knock into others more. So this is where they're getting this idea that they're knocking and colliding into their neighbor. But you've also got free electrons, and they can move. And if they gain energy, they will gain more kinetic energy, and they will move faster because they've got more energy because they've been heated. And again, they collide because they are free to move, unlike the neighboring atoms. They can collide into neighboring atoms. They can collide a little bit further down. You know, they are much, much smaller. So they can get through quite a lot before they collide with an atom. And they can collide, and their kinetic energy of the electron gets transferred into the vibrations of the atom, and they move more. So that's in the solid base. Convection then occurs inside the water. It occurs inside the fluid because the particles can move around. And they move around because they have different energies, and therefore the volume that the particles occupy expands. So let's have a look at this. So the water in contact with, inside here now, in contact with the base will become warmer by vibrations next to one another. But then as that gets heated up, the water in contact with the metal gets heated up. The particles themselves don't expand, but the space that they occupy because they are vibrating more gets bigger. The space expands. So it's like like cold temperature, it's vibrating a little bit. Hotter temperature, it's going to be vibrating a lot. So you're going to occupy a big amount of volume. It's like if I put the music on really loud, you want to dance around, and so you're occupying a greater volume of space. So it's not the particles themselves. You don't get bigger, all right, because you're dancing around. You're still the same volume, but you just occupy a bigger volume. And so in convection, those particles, they take a bigger volume. So we say they expand, i.e. the volume expands. It becomes less dense because density equals mass divided by volume. The mass has stayed the same, but because the volume increases, the density will drop because the density is inversely proportional to the volume. So if the volume increases, the density decreases. And in decreasing, the density gets less, and so therefore it's going to rise. So less dense hot water rises. And the rising hot water then forces the colder water to sink because it's more dense and take the place of where the hot water was. And then it kind of heats up the whole substance. Okay, I seem to be quite short on this revision session compared to the waves one, but we've looked at the triple. But you can see that whether you are triple or whether you are double, all of these questions applies. And even if you're foundation or higher, it's just ever so slightly a different approach. Remember that, you know, you've only got the three to deal with: conduction, convection, and radiation. Conduction in solids only, where the particles are fixed. Conduction is by particles vibrating and knocking on from one, and then making the neighbor vibrate more, and that knocks on to the next, and so on. In metals in specific, they've got free electrons, and then you've got convection in liquids, soups, air, the air in the classroom and how it's heated. You know, you still need particles, but those particles are free to move, unlike in conduction. In convection, the particles are free to move, so they become less dense when they're heated. They rise, take the place. And then in radiation, you're looking at black, silver. Black are good absorbers. They are poor. They are good absorbers and they are good emitters. And silver surfaces are poor absorbers and poor emitters, but they are good or at reflecting the heat energy, radiated heat energy. So not a lot of calculations in this unit. It's a lot of explanations looking at density. That's why this density is in there, because density is mass divided by volume, and that kind of comes into the convection side of things. They like you looking at, you know, experiments and relating what you see there. You might never seen that diagram there, for example, and that diagram there, you know, you just have to read it, just kind of like be open to it, and just kind of like use the information in that diagram and try and work out that from the knowledge that you've got, how it works. Okay. You might have seen these experiments, or you might have seen it on a video, or you might have actually done it, but they will be talking and asking about experimental technique. You know, how can we make, you know, the experiment better? How can we make it more accurate? How can we, what are you seeing? How can we plan for it? How can we do the control variables? So it's a nice way of bringing in practical concepts, but it's also, you know, a little bit less on the maths front, but a lot of explanation. So be prepared to talk conduction, convection, radiation. Be prepared to apply yourself to the experiment, and be prepared to kind of talk in terms of particles. So read the question thoroughly. Thank you very much for listening. That's the end of the GCSE revision sessions for now. Do go to the Carl & Cymru site for more revision sessions, and good luck with your revising.